Black holes represent some of the most mysterious objects in our universe. Although they were predicted even before general relativity was put forth, and even though thousands of them have now been spotted all throughout the universe, we can only see what happens outside of their event horizons. Their interiors are forever cut off from us by the presence of an event horizon, a boundary separating what can interact with the outside universe from what cannot. Inside of every black hole, a singularity is theorized to exist, a location where the laws of physics themselves break down, and where even space and time as we know them cease to exist. On the other hand, our universe could have initially emerged from a singularity, giving rise to a state of cosmic inflation followed by what we recognize as the hot Big Bang, the starting point for all of the known matter and radiation that's arisen within our observable universe. Is it possible that these two concepts, a forming black hole on one hand, and the emergence of our observable universe on the other, are related? It's a great idea, and it's been considered by many. While it may not be strictly true, like many ideas in physics, we can learn a whole lot and enrich how we think about the universe simply by considering it. Let's dive in. First, let's begin with black holes. They were originally put forth in the late 18th century, in the context of Newtonian gravity, when scientist John Michell was thinking about the sun. Michell recognized that if you had an object of the same density as the sun, but was about 500 times larger, the escape velocity at its surface would exceed the speed of light. Therefore, he reasoned, no light would get out, and you would wind up with a dark, dense, massive object in space, what we know as a black hole today. In the context of general relativity, non-rotating black holes were developed by Carl Schwarzschild in 1916. And the solution for physically real rotating black holes was discovered in 1963 by Roy Kerr. Roger Penrose was awarded the Nobel Prize in Physics in 2020 for his pioneering work on the astrophysical formation mechanisms of black holes, and for demonstrating the necessity of having a physical singularity at their centers. The singularity could be point-like, for non-rotating black holes, or smeared out into a one-dimensional ring, for rotating black holes. But a key point was that, if you gathered enough mass energy in one particular region of space, so that you formed an event horizon, a region from which nothing, not even light, could escape, and then demanded that everything still obey the laws of general relativity, you would inevitably form a singularity in this black hole's interior, with no exceptions. A singularity, importantly, represents a location where the laws of physics themselves, and even our understanding of the existence of space and time, break down. However, black holes aren't eternal, unchanging objects. They exist within our quantum universe, and so are subject to the rules of quantum field theory. They're also very massive objects that occupy very small volumes, and so they introduce a large amount of space-time curvature close to their singularities, including at and even outside of their event horizons. When you combine these two aspects of reality together, you wind up finding out that the vacuum of empty space outside the event horizon isn't stable, but rather emits a steady stream of energy-carrying radiation, Hawking radiation. Over extremely long timescales, even if left completely alone, black holes will decay and evaporate, slowly losing mass to this form of energy via Einstein's famous E=mc2. In addition, there's something very interesting about black holes. Every point describing the exterior of a black hole, including absolutely everything that we can access and observe from outside of the ones found in our universe, can be mapped in a mathematical, one-to-one fashion to a corresponding point on the interior of a black hole. You can look at a non-rotating Schwarzschild black hole, for example, and simply by replacing the radial coordinate r with its reciprocal 1r, or more accurately, if you replace every instance of RR with RR, where R is the Schwarzschild radius of your black hole, you flip the interior and exterior of the black hole. It's as though our view of reality, what inside versus outside a black hole looks like, depends solely on the way we assign our coordinates. Now we come to the universe as we observe it. Although it's governed by the same law of gravity that governs black holes, Einstein's general relativity, there are two key differences between the spacetimes that describe our universe and the spacetimes that describe black holes. Our universe, as we understand it, is uniform on large scales. If you imagine taking a giant three-dimensional dipper, a dipper several billion light-years on a side, and dipping it into any region of space, you'll pull out the same amount of matter and energy regardless of where you dip. There will not be a preferred direction or location. All regions to 99.997% precision are equivalent. We say that this means the universe is both homogeneous or the same everywhere, and isotropic, or the same in all directions. This fact about the universe is so well established that it's simply known as the cosmological principle. And because it's isotropic, homogeneous, and filled with at least one species of matter and/or energy, this universe cannot be static and stable, as was demonstrated way back in 1922. Instead, the universe itself must be either expanding or contracting, the same way that the square root of 4 can either be +2 or -2. The equations admit both types of solution. The only way to tell is to go out and measure which one describes the universe you live in, highlighting the difference between physics and mathematics. Mathematics tells you which solutions are possible, while physics tells you which solution actually describes your physical reality. In our case, unambiguously, the universe is expanding. It might seem then that there's no way these two things could be related. How could an expanding, uniformly filled universe possibly have any relation to a concentrated collection of matter and energy, including lots of mass, that draws everything in towards a central region? After all, that's one of the hallmarks of a black hole. It's what's known as a static solution within Einstein's general relativity. In a static solution, which we'll have once the event horizon forms, space itself will appear to flow by a certain amount in a certain direction. The solar system, for example, can be treated as an approximately static solution, where the sun's mass dominates space, and hence the Earth doesn't move in a straight line, but rather follows the curved geodesic, or world line, determined by how much the sun's mass curves the space around it. Similarly, the space around a black hole, as well as the space inside a black hole, once the central singularity forms, appears to flow towards the central singularity, both inside and outside the event horizon. From outside the event horizon, it's still possible for real physical objects in our universe, matter, antimatter, radiation, or anything made of quanta, to escape out into the broader universe if they have the right velocity momentum. But from inside the event horizon, you must inevitably arrive at the central singularity. These two cases, our observable, expanding universe and the interior of a black hole, would seem to be so different when we first think about it that it's puzzling how anyone could think that they might be related at all. And yet, if we take a deeper look, it turns out that they can be much more closely related than your initial reaction might lead you to believe. One thing you can do is recognize that there's a critical mass density to any expanding universe. A density that, if you're below it, will lead your universe to expand forever, but that if you're above it, will cause your universe to reach some maximum size, stop expanding, and to eventually recollapse. When it does recollapse, all of the matter and energy within it gets concentrated into a single point of infinite density, a singularity. In other words, the end state of an overdense universe could be identical to a black hole. You can then go and measure all of the matter in the universe, including both normal matter and dark matter, and compute what the actual mass density of the universe is. You can then measure or calculate the size of the observable universe and compare, for all the mass you have within the universe within the observable volume, how big the Schwarzschild radius of a black hole with that mass would be. It turns out that such a black hole would be enormous, with a Schwarzschild radius of about 15 billion light-years. That's close to, but significantly less than, our actual observable universe's radius of around 46 billion light-years. It's also true that if you look at the equations that govern the formation of a black hole and the structure of its spacetime, you could do something fascinating. You can reverse the flow of time. We often note that nearly all equations and interactions in the universe obey a time reversal symmetry. They're the same forwards and backwards in time. Then you can ask yourself, what's the time-reversed implications of a black hole? The answer turns out to be a white hole. A singularity from which space, time, and a whole lot of matter and energy emerge all at once. Can you think of an event in our cosmic past that might be similar to a white hole? You aren't alone if you said the Big Bang, which is the closest thing we know of to such an event. All of the matter and energy in our observable universe emerged from the early stages of the hot Big Bang, and as it expanded and cooled, it gave rise to the universe we know, the universe we now observe today. It's a compelling line of thought, but two developments in the late 20th century show us that the analogy is only a loose one. The hot Big Bang itself could not have begun from a singularity, but instead was set up by a prior non-singular period known as cosmic inflation. Inflation is best described as a rapid, relentless state of constant exponential expansion, and only when it comes to an end does the hot Big Bang begin. And our universe isn't just filled with matter, including dark matter and radiation, but also a form of energy inherent to space itself known as dark energy, which causes the expansion of the universe not to slow down, but rather to accelerate. But maybe these details aren't problems for the notion that the inside of a black hole in one universe leads to the birth of a new universe within the interior of that black hole. Maybe these details are hints for how it might actually work. Consider this. We talked about Hawking radiation on the one hand, as the way that black holes evaporate over very long timescales. Now, we just brought up the fact that in two different epochs, one preceding the Big Bang at high energies and one causing the late-time accelerated expansion of the universe at low energies, it seems that there's a form of energy inherent to space itself. Could Hawking radiation from a black hole in one universe potentially be related to some form of dark energy inside the baby universe that gets birthed inside of it? Let's think about it. Black holes gain mass as material falls into them, and decay, losing mass, via Hawking radiation. As the size of the event horizon changes, it may be plausible that an observer inside that event horizon, corresponding to an observer within the baby universe, sees the energy inherent to their fabric of space change as well. Perhaps the current hints that dark energy may be evolving within our universe actually point towards this scenario, and represents the event horizon of our parent black hole either growing or shrinking over time. One remarkable fact about the astrophysical black holes we've actually found within our universe is that they're all, to the best we've been able to measure them, not only rotating, but rotating quite rapidly. One remarkable question you can ask is this: if you're an observer who falls into this black hole and crosses the event horizon, what will you actually observe happening around you, assuming you remain intact and aren't destroyed by tidal forces? The answer, as worked out by University of Colorado astrophysicist Andrew Hamilton back in the 2010s, is that when you approach or reach the inner event horizon, because rotating black holes have their event horizons split into inner and outer event horizons, you wind up seeing something that looks an awful lot like the epoch of cosmic inflation that gave rise to the observable universe. Meanwhile, within the black hole itself, you do get a collapse to a space-like singularity. It's plausible, by following many different lines of reasoning, some more mathematically intensive than others, to think that there might indeed be a connection between the birth of our universe and the creation of an extremely massive black hole from a universe that existed before our own, and the formation of black holes within our observable universe and the creation of baby, pocket universes inside each of them. These ideas themselves are still speculative, as what we're hoping to do is to link robust, unambiguous mathematical predictions with directly observable parameters within our universe itself, but worth developing and pursuing further. Finally, throughout history and including at present, some have suggested that our universe may actually be rotating, albeit on scales larger and timescales longer than we can presently measure. Now recall that a Kerr black hole is the solution for a space-time with a black hole that rotates. As illustrated above, the faster the rotation, the greater the asymmetry between the various dimensions a black hole exists within. If dark energy turns out to be anisotropic, or different in different directions, which is something that the completed but currently insufficiently funded for launch Nancy Grace Roman telescope should find out, it could wind up providing indirect evidence that points to our ultimate cosmic origin as being the interior of a rapidly rotating black hole. Despite the fact that it would be easy to say, no, black holes have these properties, and our observed universe has these other distinct properties, and therefore they're not related, that reasoning is too simplistic. The fact is that we don't understand everything there is to be understood about our universe, and that these lines of thought are not only still valid, but, along with many others, are still being actively pursued today by legitimate researchers in the fields of astrophysics, cosmology, general relativity, and fundamental physics. I can't tell you whether there's any validity to the idea or not. That's not something science knows at present. All we can say is there are reasons to keep investigating it, and hopefully someday, we'll understand the universe well enough, through a combination of theory, experiment, and observation, to figure out whether and how a black hole's interior relates to the universe we inhabit.